Hi, this is Dr. A.K. Srivastava. In this video lecture, I am going to discuss Hall effect. I will also calculate Hall coefficient, charge carrier concentration, resistivity of the material, conductivity of the material, and mobility of the charge carriers. So let us first define this Hall effect. So to define Hall effect, I have taken a p-type semiconductor here. This is p-type semiconductor. And connect this p-type semiconductor through a battery. And suppose that Ix current is flowing in this semiconductor from C to D. Now suppose that length of this conductor is L and width of this semiconductor is W and T is the height of this semiconductor. Now what is the direction of the electron? Direction of the motion of the electron will be in this direction. Electron will flow in this direction. So I am showing some electron here in this block, semiconductor block, and positive charge, or you can say holes, they will move in this direction from C to D, means direction of the current. Okay. Now after that, apply magnetic field Bz perpendicular to this block, or you can say I am considering here as along the Z direction. This is Z direction. Okay. Because of this magnetic field, electron and holes will experience Lorentz force, or you can say this magnetic field exerts Lorentz force on the charged particle. So what is the direction of the Lorentz force? That we will calculate using right hand palm rule. Right hand palm rule. What is right hand palm rule? Just stretch your right hand and direct all your fingers toward the magnetic field, that is along Z direction. This thumb along the direction of the current, that is along X axis. This palm will tell you the direction of the force on the positive charge particle, and the electron will experience force exactly opposite to this. Okay. So what is the direction of Lorentz force on the charged particle? This will be the direction of the force, Lorentz force, in this direction. Okay. And electron will experience Lorentz force in this direction. What will happen? Because of this Lorentz force, these positive charges start drifting towards the A side of this block, and negative charge, that is electron, they start drifting toward the B side of this block. What will happen? A potential difference will be developed. Potential difference between A and B will be developed. Let's suppose this potential difference is VAB. Okay, this is known as Hall voltage. Hall voltage. An electric field will be established from A to B. I have written here as EY. The induction of this electric field is basically known as Hall effect. Okay, the induction of this electric field is known as Hall effect. Okay, so after some time, what will happen? There will be equilibrium, and there will not be any force acting on these charges. Okay, so what will happen at equilibrium? This is, let's suppose there is a positive charge. I am considering here only positive charge. You can consider later on electron also. Suppose that this holes having charge Q, so there will be magnetic force along this direction, QV Bx sin theta. So theta I am taking Bz, theta I am taking as 90 degree, because this velocity is perpendicular to magnetic field. And what is the electrical force? Electrical force will act in this direction, Q EY. So at equilibrium, what will happen? These two forces will be equal. Okay. So let us first calculate the force acting on charge Q along y axis. force acting on charge q along y-axis. So along y-axis, how much force is there? QEY is the electrical force minus force along minus y direction, that is Vx Bz. Let's suppose this is equation number 1. At equilibrium, what will happen? After some time, there will not be any force on the charged particle. I'm taking this charge q, that is holes. So there will be no force on this charge. So now the equation 1 you can write like this, that is QEY minus QVx Bz is equal to 0, or EY is equal to Vx Bz. This is equation number. Okay, this is the electric field. Okay, what is the current density of the holes? Current density of holes, let's suppose it is Jx. J is equal to Q P naught Vx. What is this P naught? P naught is the number of holes in unit volume. Number of holes in unit volume, or you can say hole concentration. Q is the charge of the hole, and Vx, what is Vx? Vx is the drift velocity of hole. Drift velocity of holes. Okay. Let's suppose this is equation number 3. Now substitute the value of Vx from this equation in equation number 2. What we have? From equation number 2, you have Ey is equal to Vx. Vx is what? Jx divided by Qp naught Bz. Then this you can write like this: Ey is equal to RH Jx Bz. Equation number 4, where RH is equal to 1 by Qp naught. This RH is known as Hall coefficient. This is important relation and can be asked in MCQ also. Let's suppose this equation is 5. Now let us calculate charge carrier concentration, hole concentration. Hole concentration in semiconductor. How can we calculate? I am going to use this equation number 5. So P naught you can write like this: 1 upon Q into RH. Okay. Now I am going to substitute this value of RH from equation number 4. So this will be equal to Jx Bz divided by Q Ey. Okay. Now how can we calculate this current density? Current density you can calculate Ix divided by W into T. What is W into T? W into T you can see in this diagram. This W and this T. What is this W and T? Is the area. Okay. So J is equal to I upon A into Bz divided by Q, charge of the hole, Ey. Now how can we calculate this Ey? Ey. Just look this diagram. EY means electric field between this A and B. So EY is equal to, we know the potential difference between A and B, VAB, and we know the width of this block also, W. So this you can calculate, means VAB divided by W. Okay, this is equation number 6. All these quantities we can measure, means current we can measure using ammeter, magnetic field we can measure by using Gauss meter, W and T we can measure, and this potential difference we can measure using voltmeter. So P naught we can calculate, how many charge carriers are there in semiconductor, that can be calculated using this relation. Now I am going to calculate resistivity of the material. Resistivity of the semiconductor. How can we calculate resistivity? That is, rho is equal to R A, area W into T. Rho is equal to R A over L. How can we calculate resistance? The resistance of this semiconductor, when calculated, R is equal to V upon I, that is potential difference between C and D, and current, that is Ix. This is CD, not AB, just C, because current, this Ix is flowing from C to D. Okay, so VCD divided by X multiplied by WT divided by this L. Okay, so VCD we can measure using voltmeter, and Ix current we can measure. So in this way we can calculate resistivity of the material. Now how to calculate conductivity? Conductivity of the semiconductor. So sigma is related with the resistivity, that is 1 by rho, and this is also related, conductivity is also related with mobility, that is Q P naught mu H. What is this mu H I am considering here? Mobility of the hole. This is mobility of hole. Okay, so using this relation you can calculate conductivity also. What is mobility? Now I am going to calculate mobility also. So mobility of hole is given by, so mu H is equal to sigma upon QP naught. What is sigma? Sigma is equal to 1 by rho. Okay, and Q is there. What is P naught? So P naught I am going to use this relation, but for P naught I am going to use equation 5. So P naught is equal to 1 upon Q RH. 1 upon Q RH. So this Q and Q cancel out. This will be equal to RH upon rho. Okay, so using this relation you can calculate mobility of holes. Thank you very much for watching this video.